This video here is meant to serve as an introductory discussion on something called RC circuits. The R stands for resistance, the C stands for capacitance. So these are circuits that have both a resistor and a capacitor in them. So we're going to sort of look at what some of the consequences are when you build circuits like this. So to start this out then, we'll just start out with a circuit and ask a question about it. Suppose I have a battery like a voltage source here, and I have it connected more or less across the capacitor, but I have a switch in the way. So the question is when I close this switch by pushing down on it, how much time goes by, do you think, before the capacitor is fully charged? So in other words, from the moment I do this, I close the switch, and I start counting alligator 1, alligator 2. How long is it going to take before this capacitor here is completely charged and no longer accepting any charge until it gets the charge Q is equal to CV, which is the definition of capacitance? How long does that take? Well, it turns out for a circuit like this, it'll be very quick. It'll be on the order of like 1 nanosecond, like 1/1000th of a second or something, depending on the value of the capacitance. But for just some garden variety capacitors that you pull off the shelf and so on in an electronics laboratory, it'll just be very quick. So very fast for sure. Okay, no problem there. Okay. So what I can do then is, suppose I don't want to fill that capacitor so quickly like that. Suppose I wanted to slow it down. Well, we know what slows down electric charge, the flow of electric current. It's what a resistor does. So I'll put that switch back in here again. And before I make it go onto the capacitor, I'll pass it through the resistor, which has a resistance R here. I should make those zigzags a little more pronounced there to fully reflect the symbol of the resistance. So here's the resistor here, and it goes down and flows onto the capacitor plate just that way. So here's an R, and here's a C now. So the question now is, how long does it take now for the capacitor to become fully charged? The question is a bit vague, but the answer that you should have in your head is it takes a time, they usually call it tau in physics texts and stuff, which is the product of R times C. So that's right, if you just multiply resistance in ohms times capacitors in farads, you actually get a second, you actually get a timeout. And that's how long it'll take. So it turns out the charging cycle looks like this. It doesn't happen instantly, but you get a little bit of charge on here, and then it'll get more and 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 more until it's fully charged, but it takes a bit of time. In fact, the charging, if you look at the charge as a function of time across the capacitor that's charging, so there's Q and there's T, it turns out that the charge will start at 0 just when the switch is closed, and it'll build up and build up and build up and build up and eventually saturate like this. It'll eventually stop when the capacitor is full. So that's why I said it's a bit vague to figure out exactly when the capacitor is full, because it sort of asymptotically approaches its full charging state right here. And saying T is equal to RC is when it's full is often only about the 67% point, which might exist right about in there. So when it's about 67% full, that's when 1 T equals R times C has passed. So the question is, well, what functional form does this possibly have? What does the charge as a function of time look like? Well, it looks like this. Charge will be a function of time, and there'll be some overall amplitude times 1 minus e to the minus t over RC. It'll look just like this. This is the capacitor charging function, the capacitor charging equation that exists when you close a switch and get a capacitor charged. So Q naught is, of course, the maximum charge we ever expect to get across the capacitor, which is just C times V. So whatever the maximum voltage is times the capacitance is what Q naught would be. And then this funny form in here, this 1 minus e to the T over RC, this is the form of this charging equation right here, this charging form that we see. So we see that when T is equal to 0, when the switch is just closed here, e to the 0 is just 1, and 1 minus 1 is 0. So at T is equal to 0, there is no charge on it. The charging cycle has just begun. That puts us at that point right there. Now if we wait long enough, so what is Q at time is equal to infinity? Well, e to the minus infinity is 0, so it's just Q times 1, or just Q naught. Q naught, which equals C times V. So we start at 0, and the theoretical maximum is C times V, but that's asymptotically approached because of the way this exponential function works in here. So you may have plotted these in your math course or seen them before. This is known as exponential growth, and that's what the charging cycle looks like in there. That's how charge gradually appears on capacitor plates. And it does depend critically on both R and C. So for instance, suppose I made a few graphs like this, and I had one charging curve that looks like this. If I increase the resistance even more, I can slow that charging down to look something like this, to just barely start creeping up. And if I decrease the R maybe to something very small, I can get very fast charging curves that look like this. So here's where R would be very big, and here's where R would be very small. And so this R in here is sort of like a medium or a mid-range R. And that's the way the charging curves would work. And of course, this is charge here as a function of time. So the capacitor no longer charges instantly, but takes a little bit of time to reach this maximum over here, maximum charge that is. So the other sort of interesting thing then is, like, if you know what the charge on the capacitor then is, what current flows through the circuit? Like, if you wanted to know what this current would be, what would the current be through a circuit like this, given that that charge is flowing on the capacitor plates? Well, we know that that current then is dq dt, because current is just the change in charge over time, or the derivative of charge with respect to time. So I want to know what that would be then. Let me go ahead and write out my charge here. Well, okay, what's d by dt? 1 minus e to the minus t over rc, something like that. And there's a q naught out in front. So if I sort of did this derivative here and got it all to work out here, what I'd be left with then would be some maximum current I naught times e to the minus t over rc. You can see how the derivative of a constant is just 0 in there, and then when I differentiate this with respect to time, I get the same thing, but I bring out a minus 1 over rc. And so if I have q naught over rc, we just, as an amplitude here, we just collectively put that all into I naught, some maximum current. But what's so interesting about this now is that, unlike the charge, which builds on the capacitor plates like this, the current that actually flows in a circuit looks a lot different than that. If here's the current, here's the time now, here it eventually starts very large. In other words, when you initially close the switch, there's no charge on the capacitor plates, but a lot of current is flowing through the circuit here to get that capacitor to charge up. So it starts out very large, but just as quickly as the capacitor charges up, the current in the circuit starts to drop and drop and drop exponentially like that, down to 0 like that. So it looks very much like this. If I want to sort of stack these along a vertical graph, which is pretty instructive like that, here's charge as a function of time, and there's the current there. As the charge grows, the current drops. And when that capacitor becomes maximally charged or fully charged like this, the current has dropped down to 0 like this, because there's obviously the capacitor is fully charged and there's no more need for any current to flow. So capacitors are sort of weird things like that. When they're empty, they have maximum current flow around them, and when they're full, they abruptly stop all current from flowing. And that's what the charging and the charging cycle looks like for a RC circuit. So the next one to look at then is not just the charging, but the discharging. Discharging has some familiar features as well, or some things in common with that charging there. So the question is really just the following here. Suppose I had a capacitor here, I had a switch here, and just a straight piece of wire, and the capacitor here was completely full of charge. It's completely full like that. If I close the switch then, the question is, how long would it take the capacitor to empty? In other words, if this switch got closed here, and these positive charges tried to neutralize with a negative, how long would it take before it's empty? Again, it's going to be something on the order of like 1 nanosecond or though for the garden variety of capacitor that you'll find on your workbench, or you can buy at Radio Shack or something like that. About 1 nanosecond until it's fully discharged. I can slow that down, just like before. If I take a capacitor which is all full like this, there's that capacitor which is completely full like this, and I have a switch here, and I run it through a resistor on the way over like that. So instead of that nanosecond now, I'm going to take this capacitor which is full and run it through this resistor here, and we know that resistors have the effect of slowing down electric current here, so it's going to slow down that discharge process. In fact, the capacitor is going to be mostly discharged once again after 1 R times C goes by, because again the units of R times C are in seconds, and so after that many seconds the capacitor will be pretty close to being fully discharged, or it's going to be very slow, any slow changes from then on out. So what we get then is there is a discharge equation, and if I want to look at the charge as a function of time on the capacitor after discharge, it's going to start very high because the capacitor is fully charged, and it's going to drop down to 0 like that. That's what the charge as a function of time is going to look like on the capacitor, something like that. And the equation there is an equation which governs it here. It's going to be Q naught e to the minus t over RC. So you take that charge, which is initially very full on capacitor, so the capacitor is full with a charge Q naught like that, and it has this exponential drop-off it's going to encounter as it charges down like that. So it starts very high, has an exponential drop-off as it goes down, and it takes an infinite amount of time to become fully discharged. So like we did before, if we also look at the current that must be flowing, well, remember that current is dq dt, the time derivative of charge with respect to time. We get sort of a familiar curve in there then, so we're going to differentiate this thing. So what we get is the current here will again be some maximum current, because the derivative of this with respect to time is just another exponent. So it's going to be minus 1 over RC times e to the minus t over RC, and that Q naught in there, combined all that, those constant with just the I naught right there, we're left with a minus t over RC. So we see, unlike the charging curves, the current looks very similar in the discharging case here. There's going to be a slightly different amplitude, but when the capacitor is maximally charged and you start to discharge, there's a maximum amount of current flowing through it. And as that charge on the capacitor decreases down to zero like that, well, so does the current until the capacitor is completely empty and there's no more current that can possibly flow through that resistor. So the current, almost like the Kirchhoff's law, things that we did in previous examples on DC circuits, if you indeed go close that switch, there will be a current going through this loop like that, which is I, but it's not a steady I by any means. It starts very large when the capacitor is fully charged and drops off down to zero as the capacitor loses all of its charge. So it almost mirrors the charge as a function time on the capacitor. So you have to imagine that as this is all hooked up, the charges on this capacitor gets less and less and less and less until there's nothing left. So it's definitely a transient effect that doesn't stay on very long. And just an example here, if you replace this resistor here, say with a light bulb, if you got everything just right and you had a large enough capacitor, when you close the switch, you see the light bulb is very bright and it gradually just get dimmer and dimmer and dimmer until it's totally dark again. And that's a manifestation of the charge as a function of time getting less and less in the exponential sense as the capacitor discharges. So there you go. There's sort of, in a nutshell, your idea of RC circuits. So sort of the core time constant that you talk about here is T is equal to R times C. Now you have to look this up because it has to do with either the 63% or 37%. You'll have to look up exactly what that means depending on if you're charging or discharging. And also remember that charge is sort of an exponential thing. It discharges in this manner right here, and the charge on the plate charges up in a manner like this. So this is RC circuits in a nutshell. And this is your case for charging. This is your case for discharging. So notice that this unit of RC appears in both. There's an RC right there and an RC right there. Definitely different functional forms, but the product of resistance times capacitance is time. And that's your charging and discharging equations.